Hi students, in the last session we have seen about Ampere's circular law. Today's session we are going to see about Coulomb's law for magnetism, that is inverse square law for magnetism. Before moving to that, we want to know about the force of attraction or repulsion between the poles of the magnet. For that, consider two magnets A and B. The north pole of the magnet A and north pole of the magnet B, when it faces towards each other, it repels. Similarly, when south pole of the magnet A and south pole of the magnet B, when it faces towards, then it repels. So it is clear that like poles repels with each other. Now let us consider the pole A of the first magnet and south pole of the second magnet. They will attract with each other. Similarly, if we interchange the south pole of the second magnet and the north pole of the first magnet, it attracts with each other. It clearly shows that unlike poles attract with each other. Then these two cases is similar to that of the electric static charges force of attraction or repulsion between them. Now we can extend this. The force of attraction or repulsion between the poles of the magnet will be directly proportional to the product of the pole strength and inversely proportional to the square of the distance between the two poles. That means that F is directly proportional to QMA into QMB divided by R square into R cap. That means that QMA and QMB are the pole strength. So this resembles the Coulomb's law for static charges. F is directly proportional to QMA, QMB, R cap by R square. To remove the proportionality, we can introduce a constant K. What is K? K is called permeability of free space. This mu naught by 4 pi. Mu naught is the permeability of free space. So the equation becomes F is equal to mu naught by 4 pi QMA into QMB by R square into R cap. This mu naught by 4 pi, the mu naught value is 4 pi into 10 power minus 7 Henry per meter. Suppose if we consider the magnet in some other medium having the permeability mu, then the equation becomes F is equal to mu by 4 pi into QMA into QMB divided by R square into R cap, where mu is the permeability of the medium. Now we can extend this inverse square law for one case, that is the magnetic field due to the bar magnet at a point along the axial line of the bar magnet. For that, consider a bar magnet NS, where N is the north pole and S is the south pole. The length of the magnet or the distance between the two poles is 2L. C is the midpoint of the bar magnet. Now consider a point P along the axial line of the bar magnet at a distance of R from the midpoint of the magnet. Now we can find the total force experienced at the point where we kept the unit north pole due to this entire bar magnet. If you want to find, then we want to calculate the force experienced by the unit north pole due to the north pole of the magnet alone. Then similarly, the force experienced by the unit north pole kept at that point due to the south pole of the magnet. We can calculate that. First we can calculate the force experienced by the unit north pole and because of the north pole of the bar magnet. If we find that Fn will be equal to mu naught by 4 pi Qmn divided by R minus L the whole square, where Qmn is the pole strength. Similarly, we can write this as the force experienced by the unit north pole due to the south pole of the bar magnet as Fs. This Fs can be written as minus mu naught by 4 pi QMB divided by R plus L the whole square. This minus sign, that is negative sign, indicates that because of this the force will be towards the south pole of the bar magnet. But if we see that because of the north pole, Fn we will be writing as positive. Due to that, the force, the direction of the force experienced by the unit north pole will be along the axial line, that is away from the north pole. That's why we are putting negative sign for the force experienced due to the south pole. Then we can find the total force experienced by the unit north pole kept at that point due to the entire bar magnet as F is equal to Fn plus Fs. If you write that, then we will get mu naught by 4 pi into Qn by R minus L the whole square minus QMB divided by R plus L the whole square. Then if we find that then the total force F is equal to mu naught by 4 pi into 4RL into Qm divided by R square minus L square the whole square. 4RL Qm, where Qm is the pole strength. Since the pole strength of the north pole and south pole are equal, we replaced QMA and QMB as Qm. So we get F is equal to mu naught by 4 pi 4RL Qm divided by R square minus L square the whole square. Now we can simplify. We can write the expression as F is equal to mu naught into 2R divided by 4 pi into 2 into Qm L divided by R square minus L square the whole square. Here 2L into Qm is nothing but magnetic dipole moment. So we can replace this as Pm. Pm is equal to 2L into Qm. That is the product of any one of the pole strengths into the distance between the two poles. So the expression becomes F is equal to mu naught into 2R divided by 4 pi into Pm by R square minus L square the whole square. As the next step, if we compare the distance of the point along the axial line of the dipole from the midpoint of the bar magnet, that will be too large than the distance between the two poles. That's why we can eliminate the L. So we write this as F is equal to mu naught into 2R divided by 4 pi into Pm by R power 4. If we simplify that, finally we will get the result as F is equal to mu naught into 2 divided by 4 pi into R cube. So this is the total force experienced by the unit north pole kept at that point, which is at a distance of R from the midpoint of the bar magnet. So if you see that the F will be equal to mu naught into Pm divided by 4 pi R cube. From this example, we can clearly understand that the Coulomb's inverse square law is applicable for magnetism also. So many examples we can tell. Then we can consider the gravitational law for attraction. That means that every object in the universe will be attracting every other object with a force which is directly proportional to the product of the two masses and inversely proportional to the square of the distance between the two masses. It also obeys inverse square law. Similarly in sound, that is in acoustics, let us consider the intensity of the sound. We want to find the intensity of the sound which will be varying according to the distance, and it obeys inverse square law. We already know that the pressure, the acoustic pressure is inversely proportional to the distance of the point from the source of sound. So we can write this as P is proportional to 1 by R. Similarly, if we see that the velocity of the sound at a distance from the source of sound, it is also inversely proportional to the distance R. If we compile both this, PV is proportional to 1 by R square. It clearly tells that the intensity of the sound is inversely proportional to the square of the distance of the point from the source of sound. So it also obeys inverse square law. Similarly, we can extend the inverse square law, that is the force experienced at a point which we kept unit north pole from the axial line of the bar magnet. If you find that will also obey inverse square law. These are the good examples for inverse square law, and Coulomb's law is applicable for magnetism. That is, inverse square law is applicable for magnetism. That's why so many examples we can consider for this inverse square law. Therefore, we can conclude that in science, this inverse square law is applicable for any physical quantity which will be varying with respect to that of the distance of the source. In this session, we have seen about Coulomb's inverse square law for magnetism. At the end of this topic, we came to the end of the lecture series, which consists of 8 topics starting from Coulomb's law, electric field intensity, electric potential, Gauss law, the electric potential due to an electric dipole, Biot-Savart law, Ampere's circuital law, and finally Coulomb's inverse square law for magnetism. At the end of this series, we studied about the basics of the title Electromagnetic Theory. In the future series, we are going to see some interesting topics under Electromagnetic Theory. Thank you.